Howdy friends! It is my pleasure to welcome you to a video on how the hell does the computer recognize that this image contains the digit 4, or convolutional neural networks. Spoiler alert, it's all maths. So, what exactly is a CNN? If you manage to Google convolutional neural network without making a typo like me at least a million times during the makings of this video, you'd find something like this. Oh, it's just a multilayer perceptron, an interested viewer might say. I'm sure there was at least one. And they'd be correct. What differentiates an MLP from a CNN is this, the highlighted thing, a convolutional layer, hence the name, obviously. To fully understand how does this all work, we need to talk about 4 things. Convolution, fully connected layers, and flattening. And I also flipped those two. So let's just jump right into it. Pooling. Pooling is a downsampling operation that reduces the dimensions of the image while mostly preserving the overall features in the image. An example could be max pooling or average pooling. For the sake of me not calculating averages in my head and embarrassing myself, let's show max pooling. You can imagine max pooling as, for example, a 2x2 sliding window that goes through the image left to right, top to bottom, looking at every value inside of it and preserving the highest value, hence the name, max pooling, again. If we look at this example, we would first look at this 2x2 square. We see that the highest value is 0.09 or 0.9 in this case. So we would preserve it and it goes into our final output. Then we would slide our 2x2 window to the right and we start looking at this window, the highest value being 0.5. So we preserve it, and so on and so forth. And this is how looks our final output. Here is how that would look on our example of the digit 4. Remember the sliding square? It's gonna come up again shortly. Now you might ask, why do we do this? Don't we just lose data in the process? And the answer is very much yes. Yes, we do. However, we retain the most important features while scaling the input down. As we will talk about soon, there is a lot of computation that will happen on each of those pixels. And if your input would be, for example, a 4K image of a cat that has more than 8 million pixels in it, it wouldn't be exactly cost effective. Now that we have all of this out of our way, let's talk about convolution. The convolutional layer can detect patterns in the image, from simple things like edges, shapes, up to objects or even animals. The rule of thumb is, the deeper the layer, the more complex the pattern it can detect. But how does it do it? Well, it's maths. Each convolutional layer has a set number of filters, also called kernels. A filter is like a small window that scans through an image from left to right and top to bottom, as we've seen previously. These filters are represented as matrices, with set numbers of rows and columns. Let's look at a simple example. This is our input image. It has 6x6 pixels, aka 36 pixels. And this is our 3x3 kernel or filter. Depending on the feature we want to detect, we would use a corresponding filter. For example, if we wanted to detect a left edge on the image, we would use left edge filter, or one of the alternatives. Now, let's do convolution. We have a 3x3 kernel, so we look at the first window of 3x3 pixels on our image. We multiply the pixel in position 0, 0 with the value in the position 0, 0 in kernel, and then we move on to 1, 0, 1, 0, 2, and so on. After we finish with the whole 3x3 window or a grid, we are left with 9 values. We sum them up and we get the final value. That's going into our feature map. Then we slide our window by 1 pixel to the right, and so on and so forth. For the sake of me not doing math on the whiteboard, I've borrowed this animation, which shows how the convolution is done on an image. After we went through the whole image, we are left with a feature map that highlights certain features while playing down others depending on the chosen filter. As you can see, our output is also downsampled. This is because we just did a valid convolution. If we wanted to preserve the dimensions of the input, we'd use same convolution, which incorporates padding. Let's look at the animation of convolution operation on our example of 4, using left, right, top and bottom edge filters. We can see that each of the resulting feature maps highlights certain edge, with red being the highest value and blue being the lowest value, even a negative. As a rule of thumb, we don't want to keep negative values as they highlight the negative or opposite of what we want in our feature map. So let's look at our next step, which I also forgot to write on the lists. Sorry. Activation functions. Activation functions, as the name suggests, are functions that calculate the output of each node in a neural network. In our example of 4, the result of the convolution have pixel values from -4 up to 4. As mentioned before, we do not want the negatives. As our activation function, we could use something called a rectified linear unit, or ReLU for short, which I'm not sure is that much shorter. That would be something like this. The result of each convolution operation is the coordinate on the x-axis, and the corresponding value of the y-axis becomes our output. As we can see, the negative values become 0, while the positive numbers remain unchanged, which means that our final feature maps are almost ready. Flattening. The final step before we can feed these feature maps to the fully connected layer. As the name suggests, we are literally gonna flatten the feature map from a 2-dimensional array or vector into a 1-dimensional one. For example, this. Now we are ready for the final part of the convolutional neural network, that being the fully connected layer or layers. After flattening, we are left with a 1-dimensional vector that is fed into the fully connected layer. The size of the final vector corresponds to the number of input nodes. Here we have an example of a 4x1 vector, so we have 4 input nodes. Then we have our dense layer. The number of neurons in these dense layers vary on many factors and can be optimized using something called hyperparameter tuning. Let's just say we have like 10. Each of these nodes are fully connected to the next or previous layer, hence the name. Again, these connections are called weights, or W. It will come up again. And represent the strength of the connection between the two neurons. For each neuron in the densely connected layer, a weighted sum is computed. If we spoke maths again, it would be where Z is obviously the weighted sum, X is the input, W is the weight, and B is the bias term. We go from 1 to the number of input nodes, or the nodes in the previous layer, in this case 4. The result of a weighted sum and bias addition is passed through an activation function. The choice of an activation function can be, again, ReLU, sigmoid, or another nonlinear function. The activation function gives us a final output for a said neuron. And then we have the final or output layer, and I'm also just realizing I forgot to draw the weights. Well, that's pretty. And then we have the final, or the output layer. Since we are classifying digits from 0 to 9, our output layer would have 10 output neurons. In this case, we just have 3 because I'm lazy to draw. The activation function of the final layer is usually a softmax function, which, if we spoke maths again, would look like something like this. In math words, we take the standard exponential function of each element z, or our input in this case, divided by the sum of these exponentials. The result is a probability distribution where all the probabilities add up to exactly 1. In other words, the output of the neural network will be a probability for each digit. And this is pretty much it. This is how a computer can look at a picture of a digit 4 or a cat and know what is in it, using maths.